Chavez, and today I'm going to be presenting on the effects of sleep deprivation on the brain. I'm going to give a quick outline of what I'm going to talk about today. First, I'm going to explain which parts of the brain are affected by sleep deprivation. Then, I'm going to talk about previous research on this topic. So, to begin, here we have a quick overview of all the parts of the brain that are affected by sleep deprivation, but today I'm only going to focus on two. The temporal lobe of the cerebral cortex is associated with the the process of language. During verbal language tests on subjects who are fully rested, functional MRI scans show that this area of the brain is very active. However, in sleep-deprived subjects, there is no activity within this region. The effects of this inactivity can be observed by the slurred speech in subjects who have gone for prolonged periods with no sleep. According to Chris Hembeck, PhD, 2010, the frontal lobe is one of the most fascinating sections of the brain with relation to sleep deprivation. Its functions are associated with speech as well as novel and creative thinking. Sleep-deprived test subjects have difficulties with creativity. Instead, they tend to choose repetitive words. Also, a sleep-deprived individual is less able to deliver a statement well. The subject may show signs of slurred speech, stuttering, speaking in monotone voice, or speaking at a slow pace than usual. Now, I'll be talking about the previous research on this topic. So, the first researcher, Giulio Taranti, MD and PhD, 2008, and his group have used a molecular approach to investigate what happens during sleep. They have screened more than 15,000 genes to identify all those who express changes during sleep compared to waking, and also after sleep deprivation. Taranti and his colleagues set up an experiment to identify gene expression changes related to sleep and wakefulness per se, as opposed to simply day and night. To do so, they placed electrodes on the skull of rats, who are nocturnal animals, to detect their sleep and assign them to three groups. Rats who were allowed to sleep spontaneously were sacrificed at 6 p.m. during their usual sleep period. Sleep-deprived rats were killed at the same circadian time after having been kept awake by playing with them for 8 hours. Spontaneously awake rats were killed at 6 a.m. during their usual waking period. The investigators found that while 10% of genes expressed in the cerebral cortex do change in their levels of expression during day and night, about half of them do not because of the circadian time, but because of wakefulness and sleep, regardless of time of day. This suggests that sleep may serve some cellular function, even when it has not been observed electrophysiologically. Investigators have found specific categories of genes that are selectively expressed in the sleep and in the wake brain. The genes associated with wakefulness include mitochondrial genes involved in energy metabolism, those involved in acquiring new memories, and stress response genes. Sleep-related genes are also found to be involved in consolidation of memory. In another line of work, Daniel Press, MD, 2007, and his colleagues at Beth Israel Medical Center in Boston sought to determine the effects of chronic sleep restrictions on cognitive function, in particular on working memory. Working memory is the maintenance of information in a short-term buffer for later manipulation to guide behavior. The investigators studied the working memory capacities of individuals who were restricted to 4 hours of sleep per night for 9 nights. 7 of the 12 participants in the sleep study slept 4 hours each night. 5 slept 8 hours. Every morning, participants completed a computer task to measure how quickly they could access a list of numbers that they had been asked to memorize. The list could be 1, 3, or 5 items long. Then participants were presented with a series of single digits and asked to answer yes or no to indicate whether each digit was one they had memorized. The speed of their response was measured. The longer it took an individual to respond, the less efficient their working memory. As it has been shown previously, it took longer for participants to respond when they had to keep 5 items in working memory than when they had to keep 1. Individuals who slept 8 hours a night steadily increased their working memory efficiency on this task, but participants who slept only 4 hours a night failed to show any improvement in the memory efficiency. A surprising finding by Elena Hairston, PhD, 2005, from Craig Heller and Rob Group at Stanford University, is that sleep-deprived rats actually performed better in a task that required localization of an easily detectable cue than did non-sleep-deprived rats. By contrast, sleep-deprived impaired performance of rats in a task requiring spatial navigation. The studies of sleep in rodents have looked at the effects of sleep deprivation during REM sleep. Dominant in the EEG of REM sleep are theta rhythms, a specific frequency that is associated with learning and believed to be generated in the circuitry of the hippocampus, a brain region involved in spatial learning. It is believed for some forms of memory, spatial information, the hippocampus acts as a temporary buffer for newly acquired information that is passed on to other brain regions over subsequent days to consolidate the information. Sleep is believed to be pivotal for consolidation of hippocampal dependent memory, and it is thought that experiences are reactivated during sleep to reaffirm the new neural connections acquired during prior waking. In Harrison's study, 40 rats were trained in one of two types of learning tasks using the Morris water maze, a plastic pool 6 feet round and 2 feet deep. Rats were placed in the pool at various entry points and could only escape if they located a platform. In the spatial learning task, the animal had to locate a hidden platform. To do so, the rat needed to have a mental map of the maze and use it to return to the region of the platform in each trial. In the non-spatial cue task, rats located an easily visible platform with a lemon odor in the pool. In this task, the platform was moved every 4 trials, requiring the animal to use search strategies to find the platform. The time it took rats to reach the platform was a measure of their performance. At the end of each training session, half the rats were allowed to sleep for only half of their normal resting phase. At the time they began their next day of training, they had 18 hours to recuperate from sleep deprivation. The rats who were sleep deprived actually did better on the non-spatial task. We interpret this as being due to decreased interference of the memory from the previous location of the platform, said Harrison. Because the platform in the non-spatial task was moved every 4 trials, the rats who were not sleep deprived used spatial cues to search for its old location. By contrast, animals who were sleep deprived, not remembering the previous location as well, may have used a simple search strategy to navigate the water maze. So why is this important to know? According to work from William Gibson and Bloomberg 2008, sleep is needed to regulate certain parts of the body, especially the brain, so that it may continue to function optimally. After periods of extended wakefulness or reduced sleep, neurons may begin to malfunction, visibly affecting a person's behavior. Thank you.